Hello and welcome to the inaugural Sentinel Innovation Center webinar. I'm Josh Gagney from Brigham and Women's Hospital in Boston, and I'll be moderating today's session. The U.S. Food and Drug Administration's Sentinel System helps to address questions related to the safety and effectiveness of marketed medical products. The Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through advanced analytics. We launched the webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan. With that, I'm pleased to introduce Dr. Katherine Liao. Dr. Liao is a rheumatologist and clinical investigator at Brigham and Women's Hospital. She's an associate professor of medicine and assistant professor of biomedical informatics at Harvard Medical School. She also co-directs the Applied Bioinformatics Core as part of the Massachusetts Veterans Epidemiology Research and Information Center. Her research focuses on integrating state-of-the-art bioinformatics approaches using electronic health record data to conduct studies aimed at improving our understanding and management of human diseases. The title of Dr. Liao's presentation is Unsupervised Approaches for Phenotyping Using Electronic Health Record Data. Before we get started, I'd like to mention that your lines are muted. If you'd like to pose a question, please type it into the Zoom question and answer feature. We'll answer questions at the end of the session. Finally, the session is being recorded and will be made available through Sentinel's webpage, which can be found at sentinelinitiative.org. Without further ado, Kat, thank you so much for joining us. I'll turn it over to you, and I think we'll need to have you share your slides.
Sounds good, great. Well, thank you, Josh, for your kind invitation, and I will share my slides. So good afternoon, everyone. Can you see my slides okay? And let me get it into slide view. Does it look good?
Perfect.
Great. Good afternoon, everyone. It's my pleasure to speak a little bit on my research applying different approaches for phenotyping using electronic health record data. And so I know that I have had the great opportunity to learn a little bit more about the Sentinel Initiative and the work that's been going on. So I wanted to start by providing some rationale for why I even got into developing phenotyping approaches using electronic health record data. My background is I'm a clinician trained in ClinEpi, started working in genetic association studies, but ended up in this field of applying bioinformatics to EHR data. And I'll tell you a little bit about how I got there. And then give a brief background also on how we arrived at using machine learning for phenotyping, talking about supervised and unsupervised approaches, and then really focus on the area that Josh had asked me to speak about, which is the unsupervised approaches for phenotyping with EHR data, and talk a little bit about the strengths and limitations. So the story I'd like to begin with is back over a decade ago with the I2B2 project, the Informatics for Integrating Biology in the Bedside project. This was the brainchild of Zach Kohani, who you see here. He's now the chair of the Department of Biomedical Informatics. And he had this vision. This was, back when we were just adopting EHRs, saying, there's going to be all this great clinical data there. We should be using it more efficiently for research. And so what he did was amass a team of many people with many different backgrounds: bioinformaticians, biostatisticians, database programmers, clinical researchers. You'll see a bunch of us over here, and literally put us in a room for 3 hours once a week and said, okay, figure it out. Figure out how you're going to take the EHR and all the data in the EHR to do research. And so I was a clinical researcher, and I was very interested in studying rheumatoid arthritis and heart disease, as well as what are some of the genetic risk factors that lead to both diseases. And so was very interested in this project and thinking how we might use the EHR to answer these questions. And so you might think, well, why do the EHR first? So for certain conditions such as rheumatoid arthritis, the prevalence of the disease is about 1%. So we did have a prospective cohort study at the Brigham recruiting patients, and it took about a decade to recruit 1,000 patients with rheumatoid arthritis. So you can imagine, to do other studies, to do genetic studies where you need larger populations, it would take maybe 15 years to get enough patients to do those studies. So using data from the EHR provided us with an opportunity to maybe not rapidly, but efficiently identify more patients with RA for these studies. So that's one piece of the puzzle there, and I'll tell you a little bit more as we go along of why EHR. So the first step in any project is who has rheumatoid arthritis in the EHR. And it seems like a very simple question because obviously we have billing codes, and there are very well-published administrative database rule-based algorithms out there used to study rheumatoid arthritis. And so of course the first thing we did was apply it to our EHR data. So what we did is we grabbed a random 400 patients, 3 rheumatologists reviewed the charts for rheumatoid arthritis. We applied the rule-based algorithm. In this case, it's 3 ICD-9 codes with RA, or 1 ICD-9 code of RA plus 1 DMARD. And what we found is that we could not achieve a PPV, which was in the 50 to 60 range, high enough for us to be able to do a genetic study. As you know, with genetic studies, we really wanted to get a clean phenotype. And so from there, we thought, okay, we have the EHR data, we have a lot of other data available. Let's think about what data we may want to look at. So one way to think about electronic health record data or healthcare data in general, maybe just data in general, is that you have structured data and unstructured data. The structured data are usually the data that are searchable in a database. This includes ICD-9 codes, CPT codes, LOINC codes, things that many of us are very familiar with. I'd say one of the things that was really uncharted territory at the time was use of the unstructured data, things that are in the medication note, in the progress notes, in radiology reports. And as you can see, it's not limited to just EHR data. There are other types of structured and unstructured data available. And just for the purposes of this talk, we're really only focusing on the structured and unstructured data in the EHR. And I'll use EHR and EMR interchangeably. The nomenclature has changed over time, so some of our figures are saying EMR and some will say EHR. So again, the EMR has or the EHR has 2 types of data. The structured data, which are relatively clean, and for those of you who work with it, you know what I mean. It's searchable and it's extractable, but it's not necessarily clean. But it is searchable, extractable, and you can put it into a database in a format that you can use for research. When it comes to the unstructured data, though, it's literally sitting in a pile of text flat files. But as you know, a lot of important information are in there. For example, what the physician is actually thinking, what is the result of the radiology report. And the goal of this then is to transform these data into types of data that we can analyze together with the structured data. And the way we've been doing that is with natural language processing. And so briefly, natural language processing is a field of its own. It takes the computational method, it's a computational method for text processing based on the rules of linguistics. And it takes a sentence and parses it, breaks it down to parts. And depending on the NLP platform, it might actually figure out what type of word it is and try to glean what the sentence means. But as you can see here, the sentence says, I saw the girl with the ophthalmoscope. So you might be seeing the girl with the ophthalmoscope, like you're holding the ophthalmoscope. Or you saw the girl with the ophthalmoscope, meaning the girl was holding the ophthalmoscope. So there is still some ambiguity when you use NLP, and that's why it's an entire field to try to figure out how to interpret what these sentences mean. For the purposes of phenotyping, however, we use a much more simplistic approach where we really want to understand whether or not a concept is mentioned. And I'm going to just spend a little time on this slide because I'm going to return to these concepts later on. First of all, I know many people are now familiar with NLP, but it's much more than a fine command in word. For example, it can tell if you're saying that something wasn't present. So the patient has no erosions in the MCPs. And so what that means is if I'm doing a phenotyping project, let's say rheumatoid arthritis, we're looking for bone erosions, which are a hallmark of RA, and I want to know who has a mention of erosion. I don't want to count this sentence as a mention of erosions because this patient has no erosions. Another thing it can do is understand, another function is understanding inverted syntax. So colon, ascending and descending biopsy. Maybe I'm looking for everybody who's had a mention of a colon biopsy. This would get picked up. More complex function, and this is not something that we've used routinely for phenotyping, is looking at relationships. Tamoxifen is used in the treatment of breast cancer. And for the purposes of the Sentinel initiative, this might be interesting working with NLP experts to understand whether a drug is associated with an adverse event. Last but not least, a very useful feature is the ability to pick up morphologic variations and group them together. So if you're looking for smokers, tobacco, 30 pack years, past smoker, positive top, that can all fall into a bin called smoking, that this person was an ever smoker. And so what it's really doing is taking these text data and collapsing it into clinically meaningful groups and giving you an output that you can then use for research. The next thing I wanted to talk about is how we moved from rule-based approaches, such as 2 ICD-9s and a medication, to using a machine learning approach. So as I showed you earlier, when we use the ICD codes for rheumatoid arthritis, we can only get to, we did lots of different combinations. And I'll say there was a more recent combination that came out after we published our paper that did better, but it got us to maybe about a 75% PPV. So one of the limitations of that approach, particularly for rheumatoid arthritis, is that the ICD is just the PPV on it by itself is not very good. So if you were to take a random 100 patients with RA from our EHR, review their charts, only about 20 would have RA. So no matter how many ways you slice and dice using the ICD, you can only get to a certain positive predictive value. And so the general approach for that is, well, why not put in more features or variables that may be important? And we did try that. I mean, there's some key features in rheumatoid arthritis, such as age, sex, this is the diagnosis here in lab, that may be helpful. But I wanted to walk you through a few examples, or this example, as to why we moved from a rule-based approach to a machine learning approach. So in this example here, we randomly selected a group of patients from this database of people who might possibly have rheumatoid arthritis. We reviewed the charts, which is relatively easy. I shouldn't say it's easy, but it's time consuming, but it's relatively easy for us to know or to say somebody has RA or somebody does have RA. These are data that we can extract, and these are structured data we can extract from the EHR, age, sex, diagnosis code, and lab. And I'm just going to let everybody take a look at this and give you a second to see if you see any patterns in the data. So what patterns are showing that these features here are related to a chart review status that this person has rheumatoid arthritis. And so what you'll see is that in general, people with RA are generally older, more likely to be female. Most of them have the diagnosis code, and most of them have a higher level of this lab, which is anti-CCP. So that's a pattern that we as humans can see, especially with this limited data set, limited numbers, and limited features. But what I mentioned earlier is that we clearly needed more features, but we're not sure which features are going to be important. And as you all know, for algorithm training, you need more, you need a larger sample size if you're going to train an algorithm. So once you expand this data set to maybe not 1,000, but 300, let's say we ran NLP and we pulled in erosions, medications, seropositivity, all things related to RA, and now you have 200 subjects, it becomes very hard to see what that pattern might be, what you might want to put in your algorithm. So more potential features may enable more accurate algorithms. But as you all know, if you start throwing in features that are useless, it adds noise and it's not necessarily helpful for the algorithm. And so the challenge is to identify the important features and their patterns all together and figure out if you had 300 features and you're not looking at them one by one, which of those should go into that final algorithm. And this is where we found that machine learning was very helpful to us. And just to place into context, I know many on this call are probably very familiar with machine learning. Machine learning is a subset of artificial intelligence. And just to go back to artificial intelligence, it's intelligence demonstrated by machines in contrast to human intelligence. So the goal is never to figure out how to get to the answer the same way a human would. What it wants to know is the answer, and it'll figure out that model to get there. And what that means is, so machine learning is a subset of AI. What that means is that the machine learning approaches require a training set, so you need to tell it what you're looking for. It focuses on prediction in that it just will get to the answer. It's not obviously not thinking at all about causality. And therefore, the features or the variables in the algorithms oftentimes don't make clinical sense, nor is that the goal. The goal of these algorithms are to learn structure from the data. So as I showed you earlier, it's a very complex pattern recognition. And I provide a few examples below on the different approaches we've used in, at least for phenotyping using EHR data. So going back to the types of EHR data now, we have the structured data. And now we have a way to abstract the unstructured data and pull out the features we think may be important for rheumatoid arthritis. And now you have your data, could be a lot of data, and now it's time to build the phenotype algorithm. In the old days, we used to do chart review and just review the entire cohort, and that's because we had only limited access to data, but now simply not feasible. We're looking at about 7 million patients in the partners, Mass General Brigham EHR alone. And so that leaves us with really two main options. There's rule-based, which relies on human expertise to identify important features, just as I walked you through before. And the algorithm is a combination of ands, nots, and ors. And so I think rule-based is great. If you have good codes and you can run it, it's very efficient, it's fast, and it uses usually data that you can get right off the bat. So if rule-based is possible, I usually go for that. But oftentimes, especially as a rheumatologist, where we have uncommon diseases with codes that are so-so or codes that don't even exist for our diseases, machine learning has been extremely helpful. And in this approach, we use the data to help us figure out which features are important for the algorithm and then also to weight the algorithm. And so what I'm going to do first is walk you through our first generation algorithm, which was a semi-supervised algorithm, which we started a decade ago and just published kind of our latest iteration of this algorithm. And why I'm doing this is because I want to give you a sense of how we got there, because this will give you some context when I go into our unsupervised approaches. So in this semi-supervised approach, you start with the EMR, and the next step is to apply a filter. You want to apply a filter to capture anyone who could possibly have the disease. So I'm going to use rheumatoid arthritis as an example here because that's my area of interest. So for RA, the filter is any ICD-9 code for rheumatoid arthritis. Because what that buys you, I mentioned the PPV is very not so great, it's about 20%. It buys you everybody who could possibly have RA, but if they don't have the code, they are very unlikely to have ever had RA. So that way, what you're doing here between this step and this step is boosting the prevalence of the disease. And as you know, prevalence is highly linked with the positive predictive value. So if you boost the prevalence, you'll have a better chance of being able to achieve a higher positive predictive value. The next step is extracting the data. And as I mentioned earlier, we have codified data, and then we actually have a pipeline, which I'm not going to go into today, on how we extract the narrative data using natural language processing. You put that all together into a patient-level data table. And in the circle here is where we are applying the machine learning approaches in a combination of unsupervised and a supervised algorithm. And just to not go too much into detail, what we're doing here is we first create this large table of all the potential features we're interested in. And we, in the unsupervised portion, we are looking at people with a lot of ICD codes to try to whittle down. What we're trying to do here is just whittle down that feature space. In any algorithm, the more features you throw into it, the more noise you can potentially be throwing in. And there is a penalty for throwing in all these features. Ultimately, in this circle here, what we're doing is we do train the potential features against a gold standard, and this is through chart review. And that's how we decide ultimately what are the final features in the algorithm and what should their weights be. Once we have that, we take the algorithm, we apply it to the entire EMR, and then you have a predicted probability of RA for every single patient between 0 and 1. From there, when you take the predicted probability, because we did the chart review and we know the prevalence, we can figure out the threshold at which you want to threshold the probability. Let's say above 0.65, you're able to achieve a PPV of 90%, which is what we needed for our genetic association studies. But you can perhaps think about a lower threshold, let's say a probability of 0.55, where you might achieve a PPV of 85% for a pharmacovigilance study, where you'll have a bigger sample size and you'll capture more patients. And so this is kind of changes. It's a little bit different. This paradigm is different from the rule-based approach, where you have, let's just say, 2 ICDs and 1 medication. It's a threshold. You're either in or you're out. For these algorithms that we've been using, we apply a probability, and you can adjust it based on your study. And I think it also reflects in real life, in clinical practice, how there is this uncertainty or level of certainty regarding who has or doesn't have the condition. So obviously we wouldn't move to unsupervised approaches if the supervised gave us everything we needed. So there are several limitations for supervised approaches for phenotyping. And I'm just showing a few here that really pushed us as clinical researchers to move to the unsupervised approach. I'd say the biggest time sink and is doing the gold standard labels through chart review. You have to scrub them, or people have to get access, then you got to review the charts, everybody needs to agree. The notes might not always be available. It's time and resource intensive, and it really isn't scalable if you're interested in studying more than one phenotype. So it was helpful in the first stage when all we wanted to do was to create an RA cohort. We wanted to have a RA cohort where we had a good sense of the accuracy, and then we worked within that cohort. But if you wanted to, let's say, do a study on 5 phenotypes, it really is not scalable to run through all these phenotypes through that pipeline. The other aspect is that it's inefficient because you just have a small amount of labeled data and you're projecting it onto this large amount of unlabeled data. And so that made us, it doesn't mean that we don't use this anymore. It just means that what we realize is that supervised approaches have their role for certain questions or downstream applications. And at the end, I'll talk a little bit about the different ways we've been using these different approaches. So now I'd like to transition into supervised versus unsupervised approaches. And I just want to do a quick time check here. And in terms of phenotyping, how we think about these different approaches. So when you think about the different characteristics in developing algorithm, you think about, do you need chart reviews? How do you select the features that go into the algorithm? Can we use rule-based? Can we use machine learning? How's the efficiency and how's the accuracy? So basically with the unsupervised, you don't need to do chart reviews, so you save a lot of time there. Feature selection, oftentimes it's built in, it's automated, which means you're not sitting around trying to figure out what should go into that algorithm. Obviously you can't do rule-based with unsupervised because that requires manually putting together what that rule-based is. And then with machine learning, it's an option for either of these. With the semi-supervised approach, which I showed you earlier, machine learning is just part of the pipeline, or machine learning is basically most of the pipeline. In terms of efficiency, the unsupervised is much more efficient, but where at the end, particularly for clinical research studies, the accuracy of unsupervised approaches are not known. So you do, if you choose to, and oftentimes we do, is we need to do chart reviews anyway to validate. Whereas for the supervised or semi-supervised approaches, you're often working off of a gold standard, so you have a sense of what the performance characteristics are. What's the sensitivity? What's the specificity? And so now I'd like to move over to talking about our unsupervised approaches for phenotyping using EHR data. So as I mentioned, the supervised approaches were great when we were trying to establish one cohort at a time: rheumatoid arthritis, ulcerative colitis, Crohn's disease, multiple sclerosis, and we were just diving in and doing studies within the cohort. But one of the really, I'd say, innovations that happened when we started using EHRs for research is now you can do phenotypic screens. You can look, and now that these EHRs are linked with biorepositories, you can kind of say, oh, well, now I have the genetics, I have the clinical data, I want to understand the association between this genetic variant and all the phenotypes in the EHR. And there, then, you have a couple options. You can use the ICD code as the phenotypes, which is fine, but you might want to think of ways to boost the accuracy of those codes. So as you all know, the accuracy of the codes vary across conditions. So there are several unsupervised approaches out there with different applications. And what I'm going to focus on today are two that our team has developed and applied, called PheNorm and MAP. I believe that most of the interest was in PheNorm, so I will focus on that first. And so I do want to acknowledge here that PheNorm is really mostly the work of Sheng Yu, who's a former postdoc in Tianxi's lab. He's now a professor at Tsinghua University in China, and Dr. Tianxi Kai here, who is my longtime collaborator. And so PheNorm is based on an assumption that surrogate disease labels, and that is, sorry, just having something on my screen here. Surrogate disease labels that, such as ICD codes, normalized by a patient's healthcare utilization, are log normally distributed with mean dependent on the patient's true disease status. So in other words, what PheNorm is saying is that you can use the ICD codes and that they are good enough to help you distinguish who is a case and who is a control. And that ultimately you might be able to get some kind of distribution without ever inputting actual labels from chart review that this is a case and this is a control. So what's the input in PheNorm? The main features are, and these are the abbreviations I'm going to be using in the next few slides, the number of ICD codes of the target phenotype, the number of positive NLP mentions only. So again, as I mentioned earlier, there's certain features or functions of NLP that help us to know not just whether it was mentioned, like a find in Word, but that it's not negated. So for example, if I'm looking for somebody who had a myocardial infarction, and they say patient did not have an MI, that would not be counted. Or we also have the ability to remove, if they said the patient has a family history of MI, that also wouldn't be counted. And so this NLP would be run on all the notes for a given patient, and you'd kind of pull out how many times a positive mention of myocardial infarction was mentioned. The next feature is a linear combination of the ICD and NLP data. Another feature, very important feature, is healthcare utilization. And how we've approximated healthcare utilization is with the number of notes for each patient. It doesn't have to be this, it could be the number of ICD codes at partners, it's the number of encounters, but it's some way to normalize for how often an individual is using the healthcare system. Last but not least, you can add potential features, and this could be counts of medications, mentions of signs or symptoms. And this step, I mentioned that PheNorm is unsupervised. It can be unsupervised, but you can also turn it into a semi-supervised where you are actually inputting other features that you like in there. Alternatively, there are lots of knowledge bases out there where you already have lists of features. For example, you may say, I'm just going to input this list of medications from a database. That is a way to kind of automate the process and kind of make it completely unsupervised. So what happens in PheNorm? Well, in step one, you just pull out the raw ICD data or the raw NLP data. And this is kind of the distribution you might see. I believe this one is for rheumatoid arthritis. And you do see that, you know, there are a bunch of people with no RA codes, and there's a distribution of people with RA codes. And what you get for accuracy is, you know, this is the ROC curve down here. It's, you know, so-so, but it gets you started. Next, you normalize with healthcare utilization. As you can see, this step makes a big difference. Now you're really seeing these two curves, and you're seeing a difference between cases, people with RA and people without RA. And from there, you see a pretty dramatic improvement in the AUC. The last step is random corruption denoising. And this is a step where you take clusters of patients with high numbers of ICD codes, take all the features that you wanted to check, and regress it against those features, and do drop out and try to see, if you do this a couple hundred times, which of the features end up being important and should be kept in the algorithm. As you can see from there, we saw some improvements in AUC. Now the example I'm showing you on the bottom here with AUCs is with one of the phenotypes. It's not a slam dunk across all phenotypes that, you know, random denoising, the denoising step will actually lead to a significant difference. And what we noted though is that you do really get a significant gain after you normalize using healthcare utilization. And so that's something we always do in all our EHR studies, is to make sure we account for healthcare utilization. So these are some of the results from PheNorm. What you're seeing are the AUCs of 4 different diseases. So I mentioned it was unsupervised, and most of the time in unsupervised approaches, you're not building it with labels. However, for this paper, obviously, we did chart reviews. We actually had labels for coronary artery disease, rheumatoid arthritis, Crohn's disease, and ulcerative colitis. And we had supervised algorithms for these, and therefore we were able to test this unsupervised approach using the same labels. What you're seeing are the AUCs if you use the ICD, NLP, combination of ICD and NLP, and PheNorm vote is majority voting, where you take the best of the group. I know for Sentinel, you'll probably want to focus on the gain seen in ICD, and so I'll just use RA as an example here. This is, you get an AUC of 0.868. If you were to just take the raw ICD data, get to 0.9 when you normalize, and finally, when you apply the full PheNorm process, you're at 0.93. You're seeing similar results across if you did NLP alone, if you did ICD and NLP, and if you take the best of the bunch. So you're getting closer to 0.94 there. I'd say the big advancement here is that, it's just to give you a sense of the time, for supervised algorithm from beginning to end, I'm not counting the time it took us to figure out the pipeline and develop the methods, it probably would still take a few months to review the charts, to figure out the features, to extract the data, run the algorithm, and come to an agreement. When you're doing these unsupervised algorithms, you're making a lot of these assumptions. What you're doing is you're taking the data and you're just running it through the algorithm. So, you're running this in a matter of days, or, depending on your sample size. So that's PheNorm. PheNorm does have some limitations, not, terrible limitations, obviously, because it's completely usable. And in fact, PheNorm has been, as Tianqi mentioned to me, that PheNorm has been applied to the Mass General Brigham EHR data, or the copy of the EHR data called RPDR, or a version of PheNorm. But what PheNorm outputs is a linear score compared to our other algorithms, which give you a predicted probability of disease. And so why is that important? Well, the predicted probability of disease is something that we can actually use in our models. So if you think about when you create a clinical model, you're looking at the association between an exposure and an outcome. And the outcome can be yes and no, but the outcome can also be a predicted probability of disease, which is something that as clinicians and researchers, we can interpret. The other key feature or issue is that PheNorm does not identify a threshold value for classifying subjects as cases. So oftentimes for studies, when you want to create a cohort, you want to know where to make that cut to say you're a case and you're not a case. And for that, PheNorm does not automatically provide that threshold. And so you would have to go back in and figure what that is manually. So as a result, what we did is we thought about it and, really thinking about what we needed to be able to do the studies we want to do in the EHR clinical association studies, genetic association studies, doing phenome-wide association screens or phenotypic screens. We needed something that could really distinguish yes, no automatically, and really more seamlessly incorporate natural language processing data. And so I will briefly go through MAP, but just to give you a general overview, MAP is fitting a sequence of mixture models. It's averaging these models together, and then it's giving you case versus control, as well as the probabilities. So let me take you through MAP, because I think this will also give you a flavor of the resources available now to phenotype, which may be useful for Sentinel as well. So the first step in MAP is to assemble the NLP and ICD data for each PheWAS group. So what's a PheWAS group? A PheWAS stands for Phenome-wide Association Study, and this is an approach we've been using to screen for the potential clinical significance of, let's say, a genetic marker. So we have these platforms where you have the EHR linked with the biorepository. You've got the biorepository, everybody's genotyped. And so back in the day, you had to identify the phenotype and then do the genotype. But now what you can do is you can say, I'm interested in this genotype. What kind of phenotype is it associated with? So it's basically, 1,000, you're doing a regression of association between gene and all the phenotypes in the EHR. So what are those phenotypes? The phenotypes are ICD codes that have been grouped into clinically relevant groups. And this was, I would say, the group that really made this more standardized is Josh Denny and others at Vanderbilt, who really standardize how to run a PheWAS, these phenotype groups using ICD codes. And so that's a PheWAS group, and that's what a Phe code is. So for example, a Phe code, if you think about MI, especially now in the world of ICD-10s, you could have an anterior MI, you can have an inferior MI, you've got all the positions. What you really want to know when you're doing a screen is, did that person have a myocardial infarction? And so a Phe code group would have that, all those grouped into one Phe code called myocardial infarction. So that is how the ICD codes are grouped into Phe code groups. Next, what we do is map that to the Unified Medical Language System. So what is that? I was talking about these knowledge sources very vaguely before. The National Library of Medicine hosts the Unified Medical Language System, which takes all the clinical terms and kind of groups them together. So for example, atrial fibrillation and a lesser used term, auricular fibrillation, those are all grouped into a concept called atrial fibrillation. So if you're doing a study and you're interested in atrial fibrillation, you want to capture all the different variations of the ways atrial fibrillation is described. And so what it's doing then is mapping, automatically mapping those codes, atrial fibrillation, to the CUI, this concept unique identifier, atrial fibrillation. And so one key thing I realized I didn't mention is the Unified Medical Language System. The reason why it's so important is because it helps us to organize the data we get from NLP. So natural language processing there's many different platforms, but the outputs are lots of different terms. You need those terms to also be grouped into clinical relevant groups, just like you want the ICD codes to be grouped into clinically relevant groups. So UMLS does that for us, and that's a publicly available knowledge source. And so then we're mapping the ICD codes to the CUIs, the strings, and the PheWAS strings to the CUIs. And what that's doing is just making sure that you're getting all the combinations of the different ways you might say something. So let me give you an example of that here. So rheumatoid arthritis, as I mentioned, is going to be my example throughout. You have the code. This is the PheWAS code. So this is not the ICD, but this is the ICD-9 code. They all have a string. And they also all have, so what we're doing now is mapping the CUIs to the ICD, to the string, and what you're doing is trying to cover all your bases. So now what you have are all the ICD codes that are related to RA, and all the CUIs are the concept unique identifiers that are related to RA. So when you run NLP on all the charts, you're able to pick up all these concepts and map them to RA. Next, you do a joint analysis of NLP and ICD, where you're fitting multiple Poisson and log normal mixture models. And what you're getting, and adjusting for healthcare utilization, you get a probability of the phenotype. And so we synthesize all the information from all the model fittings. You get a probability of a phenotype, and what you're doing is taking the average of the predicted probabilities from all the models. And this is where we differ a little bit from PheNorm, but we are now similar to where we were with the original semi-supervised version I showed you. Everybody has a probability, and what you're doing is picking a threshold by which somebody is considered to have a condition versus not. And what MAP is doing here is it is making some assumptions on what the prevalence is to make that threshold, but what it's doing is it's, again, taking the data set that you're giving it automatically. Well, so what you have to do here now is you've got the data set, you've processed all the notes of all the patients using natural language processing. You're running MAP on the entire data set. Everybody has a probability. It's also now trying to automatically give a cutoff for which somebody does or doesn't have a condition. So how do all these different ways stack up? So at Partners, there were, through time, we've had many chart reviews for many different conditions, including asthma, bipolar disorder, schizophrenia, breast cancer, COPD. I'm gonna go through the rest here, but just know that each of these columns is a different phenotype. And what you're seeing across here is, well, this is, we also have ways to figure out which features we might want to include. So this is if we use an automated feature curation, meaning we use an automated pipeline using knowledge sources to figure out what features might go in an algorithm. And the bottom here is if you were to, and for all of these phenotypes, we manually decided which would go in. So I'm actually just gonna, for the purposes of this talk, just focus up here. In red is map, light blue is PheNorm, middle blue is NLP only, and dark blue is ICD only. So what you can see across all the phenotypes in general is that map appears to perform the best, but not in all cases. For example, here in breast cancer, you can see that the codes are quite good. And that PheNorm also performs quite well. And you might say, well, PheNorm didn't really have a way at first to threshold, but over time we have figured out a way to retrofit it to threshold who has what condition. But this just shows you that, you know, here we've automated what features go in. And so this is a pretty unsupervised approach now to just globally running map, but then comparing it against previously validated gold standard labels. So I just wanted to briefly then talk about, you know, why go through all this trouble? What are we doing with all this? Well, some of the applications include a phenomics library. And so I work with a wonderful group at the, Tianchi and I together work with a wonderful group at the VA. The VA possibly has the largest and oldest EHR in the country, following 22 million veterans worldwide. They also have I believe also the largest biobank in the United States with electronic health record data linked with genetic data, and they're you know, on the road to recruiting 1 million veterans with these linked data. So what can you do with that? Well, you could run these unsupervised algorithms across the entire EHR, and now you have the phenotypes. So you could do that with ICDs, you could do that with the phe codes, but then you can also enhance it by running either map or PheNorm. And what we've done is we've run map across, or we're in the middle of running map across all of the VA. So now we have everyone's phenotype with a higher accuracy than ICD codes alone. The other thing we're doing now is running it, obviously the MVP is a subset of the entire VA network. And so now what you'll have is a EMR research platform where you have the EHR data. Now you have the ICD codes, you have the labs. If we run map, now we have higher accuracy phenotypes across all these patients, and we have the genetic data. And this really allows us to do some very interesting translational studies, one of which I mentioned earlier, which is a phenome-wide association study where you can go both ways. You're now looking at, I'm interested in this genetic variant. What is it potentially associated with other than what we know? So the hypothesis generating exercise. And so in summary, one thing I do want to mention, actually I probably should have mentioned this earlier, is that our phenotyping approaches are meant for prevalent conditions. And that was what they were first designed to do, where they were first designed to create cohorts of anyone with the disease. They are currently optimized for EHR data, so we don't know what the performance is in, let's say, if it were administrative data alone, and the only way to know is if it were linked to EHR data. They are robust and portable. I didn't show you all the data, but not only did we run it across different phenotypes, we've run it across institutions. VA, I'd say, was our biggest stress test, but we also ran different algorithms at Vanderbilt and at Northwestern University. Supervised versus supervised really, and the approach really depends on your downstream use. So I would say if you're interested in drilling into a certain phenotype, you probably want to know very much what that accuracy is. And for cohort creation, we tend to use a supervised approach. If it's not, if there's any question of, you know, where the ICD-9 codes are so kind of like rheumatoid arthritis. But for phenotype screens, it's just not feasible to do a supervised or semi-supervised approach. And that's where we're using unsupervised approaches. And I imagine for Sentinel, where you want to be able to, in real time and quickly process and reprocess data as it comes in, you will need an unsupervised approach. And so it really depends on the downstream use. Last but not least, in terms of future directions, we obviously are thinking, even for clinical studies, you want to know if a condition is an incident disease or if it's recurring. And that's something that these algorithms are not designed for. We are, however, testing our existing prevalent algorithms. And now that we've had these algorithms for a decade, we're going back, taking the data and slicing it up to see how well these algorithms perform in catching incident disease, but not like in a narrow time window, but in a, let's say, a 1 or 2 year time window. So with that, I'd like to acknowledge my team. A lot of what I do in this space is a joint effort with Dr. Tanshi Kai over here, who's a professor of biostatistics at the School of Public Health and a professor of bioinformatics at Harvard Medical School. This is our combined core team, Brigham, School of Public Health, and HMS. And we are joined by our VA colleagues at the VA, who everybody here has had a very important part in helping us with all this work. So, you know, everything I presented today is definitely a team effort. I showed you that big picture in the beginning and this big picture at the end. It can never be done with one person alone. So with that, I'd like to thank you for your time, and I'm happy to take any questions.
Kat, thank you very much for this really terrific presentation. We'll now open up the question and answer portion of the webinar. As a reminder, all your lines are muted. If you'd like to ask a question, please type it into the Zoom question and answer feature. And as folks are typing in questions and comments, I'll get us started with at least one question, picking up on your first summary bullet point, and also at the bottom of that slide around using these approaches to identifying incident conditions. So with Sentinel, I think we'll have important use cases where it's necessary to identify both prevalent and incident conditions, in particular, thinking about adverse events that might be drug-related as incident conditions. Can you maybe just talk a little bit more in terms of how applicable these approaches are now in terms of identifying incident conditions, and what are some of the future and ongoing work that you have to expand into that?
Yeah, I would say that we couldn't use these algorithms right now for incident disease, and that's why we're testing it now, because obviously we finally figured out prevalence. Now we're trying to figure out incidence. There are approaches out there for incident disease that we're testing now. So I didn't present on those just because we don't have the data. So I would say not applicable. I wouldn't use them now for incident disease. If you want to test it, that's great. Again, the real challenge is getting those gold standard labels. If you had a nice big data set and you're able to know incidence, then and you run the algorithm, then you can see if it works. In terms of what we're doing right now, that's exactly what we're doing. So the VA is very interested in incident disease, and they do have these now gold standard data sets where if somebody had an incident MI, or within our group of partners, people are getting incident heart failure. And what we're doing is both testing our prevalent approaches and then developing new approaches for incidents. You can imagine that the data are different for incidents, and to catch incidents is very hard.
Great, thank you. We do have a few questions coming in. So the first is a question just asking you to confirm that what you described is applicable to ICD-10 as well.
Yes, yeah. So we developed this in ICD-9, and now we've retested this in ICD-10, and we've retooled all our approaches to include ICD-10.
And then related to that, another question asks, in addition to ICD diagnosis codes, do you ever use medication codes in the algorithm to define phenotypes?
Absolutely. So that's always an option. I'd say what I showed you later was MAP, where we just took the main ICD and the main CUI, but you always have the option to include medications. The reason why, and so we almost always include them in the supervised and unsupervised approaches. It just takes more time. So it depends on what you're looking. If you're looking for 3 phenotypes, you could manually say, I want to, see if any of these medications work. If you think about deploying, an unsupervised algorithm to phenotype 1,000 phenotypes at one time, then it becomes really hard to know which medication should be going for which phenotype.
Great, we have quite a few coming in, so we'll do our best to get through all the questions, but we may not be able to get to all of them today. A question from David Carroll is there a larger set of phenotypes, maybe about 100, for which PheNorm or MAP performance vis-a-vis gold labels has been published?
Larger set, so we don't have a larger set than the 16, I believe, we published in the MAP paper. So the efforts right now, so I'll just mention at the VA, what we're doing is, I mentioned that when you're creating a cohort, oftentimes we use a supervised algorithm, but it really depends on the phenotype. So what we're doing is we just run MAP at the VA, and they are actually going to go through and say, do we actually need to do a supervised? Is MAP good enough? So we're in this phenomics library project, we are going to be validating a larger set of phenotypes. But just so you know, there are 1,800 phenotypes total. And so it won't be possible to manually go through them, but we're going to go through maybe about 50 to 100 over time.
Great. The next question is, can you elaborate on why you think the current MAP algorithm cannot be applied to administrative data only? And then parenthetically, you mentioned an EHR requirement.
Okay, yeah, so it's not that it can't be applied to administrative data. It's that we haven't tested it in administrative data. So it really right now, MAP is optimized. So what I mentioned in the summary is that our algorithms have all been optimized to run on EHR data. So I would say it would be really interesting to run it on administrative data. What we need to have though are those gold standard labels to know how it performs. And I think that's why, you know, for the most part, we haven't seen, like, we don't have access to a large administrative data set. We have a large amount of people where you can confirm the diagnosis. And that's the only way we'll know that MAP is any good. But it can be. I mean, PheNorm and MAP can both be run on it. It's just that you won't know the performance.
I see. Okay. And then another question this is from Judy Marrow. You show AUC as a performance measure throughout. A key concern for us in the Sentinel context is also keeping sensitivity high, making sure we identify all of the adverse events of interest. As you showed early on, as PPV increases, sometimes sensitivity suffers. Can you elaborate on the PPV sensitivity trade-offs in the AUC statistics that you described?
Yeah, that's a very good point. I showed the AUC out of simplicity. So again, I'll say that the studies, the goal, and this is why I wanted to make sure the goal of our phenotype algorithms have really been for clinical research studies, where we want to get as big a cohort as we can get, but with a reasonable accuracy at the cost of sensitivity. So there is a way to increase sensitivity. So for all of these algorithms, the output is either a score or predicted probability. And so you could actually, depending on what your goals are, if you take different cutoffs of the probabilities, you'll get a different measure of PPV versus sensitivity versus specificity. And so, so yes, I don't have them. I mean, there were so many, but we do have those numbers for most of the phenotypes, because what you do is you take the data set and you slide that threshold at different areas. And obviously, for the most part, you are increasing PPV at the cost of sensitivity, but not always. So the drop isn't always a big drop if you go from 90 to, let's say, 95. It really depends on the phenotype. But that's the other point I want to make, is that for most of our algorithms, again, I showed AUC just because it was more simplistic, but our goal is PPV, and that's really our benchmark to know whether this is the right algorithm for us to use or not.
Mm-hmm. That makes sense. Another question, and one that came to mind for me as well, is picking up on what I think was the third bullet point on the summary slide, where you mentioned portability. And this specific question is about commenting on the application of the tools across multiple potentially heterogeneous systems. I know you mentioned Vanderbilt and other sites. And maybe if I could just add to this question, what sorts of validation or maybe limited validation do you do in the external sites as you try to transport the algorithms? Yeah,
that's a very important question. So what we found in porting these algorithms is that if you add NLP, it tends to stabilize the algorithm, narrative data. Our best guess is that the way people describe a condition is more similar to then how they code the condition in certain areas. So there's definitely variability in coding across different institutions. So what have we done for that? So in order for any porting any algorithm, you should always have a set of gold standards on the other side to make sure it's working right. And that's kind of what we do whenever we send it somewhere else. I guess in terms of what is the work going on right now to try to harmonize that, we are actually right now developing a method where you take an institution and you take all their ICD codes and you look at all the relationships between all their ICD codes. And you can imagine that each institution has a slightly different relationship between their ICD codes. If you know that pattern, if you're looking for stroke in one place and you see this cluster of codes, and you see stroke in another place and you see their cluster of codes, then you know that those are the equivalent codes. And so that's something, this is like future direction, something that we're actively working on to try to understand how to make it more portable and more portable automatically, rather than, you know, sitting down with the programmer saying, well, what are you using for this? And what do you guys use for that? That's a very good question. It's a big issue with porting algorithms.
I think we have time for one more question. And so the last question will be, what differentiates PheNorm and MAP from other unsupervised approaches that you mentioned?
Yeah, I think it really has to do with, I'd say the main difference is that we are our application for clinical research. So as I mentioned, my background is in clin epi, so we're a little crazy about understanding what the performance characteristic of our algorithms are. Whereas there's less of a emphasis on that from the other unsupervised approaches. Their applications are also different applications, and there's different data input. So I think that just not going to any individual one, but for example, one of them is saying, well, as you're feeding in data, how do you get closer and closer to what this patient might have? So that application is different from us saying, we have, you know, 22 million patients in the EHR. We want to know what phenotype they have right now as of this time.
Great. So once again, I'd like to thank Kat for presenting on today's inaugural Sentinel Innovation Center webinar. As a reminder, this session has been recorded and will be made available through the Sentinel webpage. You can also find details and registration links for future Innovation Center webinars on the website, which is at sentinelinitiative.org. This concludes our session. We hope to see everyone again next time. Thank you.
Great, thank you.